Good evening, ladies and gentlemen. Tonight, we're going to hear about astroseismology and starquakes. I think most of us here have experience or knowledge of earthquakes. Many of us also would have experience of using seismic techniques to probe the interior of the Earth. But I think very, very few of us know about starquakes and examining the interior of the stars above us. So we're really lucky tonight to have a world expert on this subject who's going to take us through this interesting topic and explain not only how we can look inside the stars, but also how this helps us understand the galaxy in which we live. It's a pleasure to be able to welcome Professor Conny Aerts here tonight. Conny is a professor at the University of Leuven in Belgium and has a professorship also at the University of Nijmegen in the Netherlands. She has a long and distinguished and prize-winning career in the field of physics of stars, especially astroseismology, but she also, in her career, contributes enthusiastically to astronomy in general and to advancing the cause of women in astronomy. Let me very briefly take you through her career. Like many professional astronomers, her interest in astronomy started when she was very young, still at primary school. She continued then on a route many professional astronomers take, doing a degree in mathematics at the University of Antwerp, and then moving on to study for a PhD. For her PhD at the University of Leuven, this involved travelling to many international observatories and taking high-resolution spectra of stars and then using advanced mathematical techniques to analyse them in order to determine the oscillations, the wobbling and the vibration of the stars. And some of the techniques that she developed then are still in use today. After her PhD, she won a grant to do research to establish her career, to establish a research career. And then if you read Conny's biography, she says, probably with a typical smile, she started off this work with a 5-month leave of absence to have her first child. So when she came back, she positioned herself in a slightly broader field, variable stars, to exploit the data from one of the satellites of the European Space Agency, the Hipparcos satellite. She was appointed lecturer at Leuven and then a full professor, and also has a full professorship, as I said, in Nijmegen. The research of Conny and her team covers a very broad field about the structure and evolution of stars. And to do this, she looks at many different stars of different ages, different chemical compositions, and different masses, and pays particular attention to their oscillations. It's a very vibrant field with lots of new data, and she's published, and with her team, many groundbreaking results, including, for example, on how the stars rotate internally. And her research was recognised in 2012, just 2 years ago, by the award of the very prestigious Franke Prize, which was presented to her by the King of the Belgians. This prize is awarded annually and to recognise the achievements of a Belgian scientist or scholar and to encourage future work, I understand. And Conny was the first woman to receive this prize in the exact sciences. I was searching the history of the prize, and it's interesting to note they've not yet caught up with it. Most of the websites still refer to the recipients, the laureates, as he. So following you, they're going to have to change that. This prize is often referred to as the Belgian Nobel Prize, and looking at the list of past recipients, I note that several of them also got Nobel Prizes. So Conny, no pressure, no pressure. So looking at your other activities, quickly moving on, she's always been willing to give back to astronomy. She's served as president and vice president of various commissions of the International Astronomical Union, the governing body of world professional astronomy. She serves on many national and international committees, and that's actually how we first met. We first met about a decade ago when she was advising the European Space Agency on one of its committees. And I remember vividly not only her forthright scientific opinions, but her determination and her ability to smile and make the room look happy the entire time, even when there were major disappointments, like ESA not being able to go ahead with a mission in her field. I mentioned earlier her determination to advance the role of women in astronomy. In her own institute, she's achieved an equal gender balance, which is much better than astronomy as a whole. I've been working with her over the last few years on setting up research workshops, and with every proposal, Conny first looks at the science. Is the science good? Then her next question always is, are there enough women involved, both as speakers and as organisers? And if not, she's extremely determined in making sure the organisers fix it. Also, I mentioned her role in the IAU, the International Astronomical Union, and there she was interviewed for a blog known as She is an Astronomer. Do you remember that? And at the end, the last question the interviewer asked her was, what recommendations would you make to young women starting the career in astronomy? And there are several very nice ones aimed at women, such as don't adapt to men's style, make them adapt to yours. But there are also ones much more general, which I think sum up Conny as a person. Do it your way, even though it's different from all others. And make sure you have a good personal mentor and follow the advice of good role models. So to finish, Conny, it's a pleasure to introduce you. I'm very pleased that with the recent selections in the ESA Science Programme, I think there are a lot of missions that are interesting to you, and we can work together. And so may I turn the floor over to you to talk to us about astroseismology and the study of starquakes and their impacts on astrophysics. Professor Conny Aerts.
Thank you very much, Martin, for this very generous introduction. And to the audience, I'd like to say it's my pleasure to be here and to be able to discuss about one of my passions, which is also my work, and that by itself is already very pleasant. So I'm hoping to bring you up to speed and make you all expert astroseismologists in 1 hour. That's my task, assuming that you are not yet familiar with this field. So here you see what this talk will be about, and I tend to speak of starquakes because, in fact, as Martin already alluded to, everybody is somehow familiar with earthquakes, and earthquakes are used to study the interior of our planet. I cannot start drilling a hole here until I reach that core of the Earth, but I would still like to know what's inside it and how it will evolve, because that's of general interest to everybody. So we are going to do the same for stars. Stars that are really billions of kilometers away from here. So as you can imagine, it's a bit more difficult to detect these starquakes. But we can do a lot with them once we do. So let's move on. You know, this goal of this study is to learn about how stars live, how they get born, how they live their life, and how they die. And we want to understand that, and we know that fairly well. In this upper plot here, you see sort of a cartoon of how the sun will live its life. So it gets born from clouds of molecules when they collapse under their own gravity. That's the general way that stars form. Then it lives a quiet life for about 90% of its time, and we're about halfway. It's just for you to know that you need not be worried about what I'm going to tell you, because there will be some less nice episodes in the life of the sun, but you will all be dead. So there is no need to worry, and also your grandchildren will probably no longer be around, because we're talking about evolutions in billions of years. And this already tells you why astronomers have to be clever. We are frustrated. We cannot watch a star, how it lives and how it dies, because it simply takes millions to billions of years. So we have to find a way to understand stellar evolution by looking at different stars in different evolutionary stages. And so at one point there will be a really global warming going on. Not tomorrow. This is not about global warming of the Earth. This is about global warming of the Sun with respect to Earth. And this is an artist's impression of what will happen. At a certain point, the Sun will have no longer nuclear fusion in its core. Stars, they are experts in nuclear fusion. We can't do that in a safe way here on Earth, but the stars have no problem with it. And that's, in fact, what directs their life. That's what gives them the energy that you can see with your eyes when you look at the nightly sky in the evening. At a certain moment, the fuel is finished, and so the star will start dying, if I may say so, and it will swell up. So the Sun will come very close to Earth, and it will be much hotter, even though Madrid was, for us Belgians, the past few days, very, very nice and hot. But this is beyond any comparison. And so we want to know how this path here goes. We want to know the details. We know more or less how stars live. We also know that some stars get born with a very heavy mass, and they will end their life as supernova explosions, big explosions. Again, nothing to be worried about because there are no such stars in our close vicinity. So we will see the explosions very far away. Stars like the Sun, they will have a very quiet death, but they will swell and become what we call red giants. And that's what's going to happen to the Sun. And we have been studying a lot of stellar quakes of red giants for this reason. Now, why do we want to bother? Because I just told you in a few minutes how stars live, so we already know. But, you know, there's an expression in English, the devil is in the details. And it's the same for stellar evolution. We can't look directly inside the core of a star, and that's where the life is being determined. So we would very much like to see inside the star, but we cannot. We only see the surface of the star. And even then, the stars for us are tiny little dots in the sky because they are so far away. So we cannot resolve the stellar surface, let alone look inside. This view is blocked from our observations. And this is bothering us because we know that the theory has shortcomings. We know, for instance, that there are massive stars like this cartoon here is trying to depict, where the life of the star seems to be longer than our theory predicts. So that's because there is not enough fuel in the core of this star. So this core region here, where the nuclear fusion is taking place, and it's only in the core because nuclear fusion needs a very high temperature and a very high density. And so these quantities, they go down as you go away from the core, and then it's too cold to have nuclear fusion. Well, we know that we are lacking some material inside this core, and we need to understand why that is. Also, and that may be good news for us, in the recent years, a lot of planets have been found around stars. These are called exoplanets. And so these planets, of course, we want to know, are there many? Are they like the Earth? Are they more like Jupiter-like gaseous planets, and so on? But what has struck us is that some evolved stars, some red giants, so some successors of the Sun, while they are dying, they have sort of still planets. Well, if our theory would be correct, the planets should have been swallowed because the stars would have eaten them up. And so that may be good news for the Earth, but it also tells us that our theory is not really adequate at this stage. And so we want to improve upon that. And how can we do that? Well, as I said, we only have observations of the stellar surface, so we would like to do something better. And then I come back to the seismologists, geophysicists on Earth. We only have measurements at the surface of the Earth, but we would like to do better. And what they do is use their seismographs to detect the earthquakes, and this provokes waves, and these waves travel all the way to the Earth core and bounce back. And so then they can be detected again. And by doing this inference, we can learn about the core of the Earth. And we are doing the same for stars now. So how does that work? Well, I love mathematics, but I might be correct in thinking that the majority of the audience is not really an expert in mathematics or in physics. So I didn't bring any equations today, only cartoons to get you onto speed without mathematical formula. So why do we do seismology? How does it work? Look at this here. Let's imagine we could cut a star into two pieces, and then the star quakes, the oscillations, they would invoke waves, and they are indicated here in the slide in color. So you have this red wave, and you have the green one, and the yellow one, and so these quakes, they give traveling waves that pass through the star. And me, as an astroseismologist, I would love to detect, well, the red wave's okay, the green and the yellow one are also fine, but I love this purple one. Because that quake gives a wave that passes all the way through the stellar core. And that's where all the action is. That's where the life is determined. So we want to hunt for these purple ones, but it's already a success if we can detect anything at all. I'm sure all of you, hopefully with protected glasses, watch the sun every now and then, maybe at sunset when it's not so strong for your eyes. The sun has hundreds and hundreds of solar quakes all the time, but you can't see that because the quakes of the sun have too low amplitude. Your eyes are not good enough detectors to see that. Yeah? Because the amplitude of these quakes are parts per million. And your eyes are excellent detectors, but not good enough for this. Okay? So that's what we have to try and detect. Now, how does the mathematics work? Let's follow this yellow wave here during many cycles, up and down and bouncing back. This is like traveling sound waves in an auditorium. Right now, I'm making a lot of sound waves. Right? And the technology helps me a bit here. And you can hear me, even if the microphones would be dead, you would still hear me talk because I create sound waves and they travel in this cavity, in this beautiful room here. It's the same in a star. You know, the star is a gaseous sphere, it has quakes, and that's comparable to sound waves. And by understanding these sound waves, we can understand the physics, because the way the sound propagates is determined by the pressure and the density and the material of the cavity, let's say, of this concert hall. Yeah. So let's say we follow this yellow wave and we follow the green one, and let's assume that we have a way to detect their effect on the surface. Well, it's the same physics, right? It's the same star. Only the green wave goes a bit deeper than the yellow one. So by subtracting the frequencies of the waves, we learned something about the area in the star that's only green and not yellow. And so if we have enough waves, we can build up the interior of the star layer by layer in terms of its physics. And that's basically how astroseismology works. And in daily life, I don't use the pictures, but I use the equations. But it's the same, okay? So, to give another analogy, which you may be very familiar with, and if I give this talk to very young kids, it always works. Huh? I hide myself after the screen, and then I play a flute. And I won't do it today, but I did bring it. I play a flute, right? And then I ask the question, what is it that you hear? And then they all shout, a flute, because they are proud that they can answer a professor. Right? And then I disappear again, and I play another instrument, which is a piccolo flute. And then, of course, I ask the question, which flute is the biggest one? The first one or the second one? And they all have it right. Because this flute has much higher tones. Right? The smaller the instrument, the higher the frequency. You all know that. So that's what we do with stars, only we can't hear the stars. The sound waves invoked by the quakes of the stars, they remain inside the cavity, they remain inside the star. So that's a bit of annoying, because else you could rely on your ears to decide about how big a star is and how small. It's just like with the flutes, okay? So what do we do in practice? Well, here is a very, oh, I went too fast here, let me go back. Here is a very simple musical instrument, let's say a guitar string, and the musician knows perfectly well, if he or she has a symphony in front of him to play, how to deal with this. He can play the string in the fundamental modes, or in the first overtone, or in the second overtone, or the third one, and so on. Yeah? So what do you do when you characterize a string that is vibrating, that is oscillating, that is having a quake, if you want to use that terminology? You need a period, that's the frequency with which this string goes up and down. You need an amplitude, that's the strength of the sound, let's say. And you need a number, and the number indicates how many notes you have, how many overtones you have, okay? So let's now move on to a star. A star is just, for me, a three-dimensional string that plays music, right? And so what do we need? We need a frequency for each mode. We need an amplitude, that's the strength, yeah? And we need three numbers, because we're now doing it in 3D. But for the rest, it's the same. So the mathematical description is really very, very similar. And so here you see three stars. These are not real stars, these are animations, of course. And so instead of knots, we have nodal lines, because it's a two-dimensional surface that you're looking at now. So all the particles in these white bands here, they do not move during the quake. They stand still. These are the nodal lines, as we call them, instead of knots, okay? So in principle, astroseismology would be simple if we could resolve the stellar surface, because we could just see it moving up and down. But we can't do that. We can only do that for the sun. For the sun, we can resolve the surface, and that's why the study of solar quakes, which is called helioseismology, has been developed much earlier than astroseismology, where we have to do the same kind of trick, but then for stars that we cannot resolve, okay? So, still I would like to come back to music, because that's very clear in your mind, I think. And I'm not a musician, so I can't play a concert. But anyway, let's move to the analogy. And I would like you to sort of get a grasp of how stars would sound if you could sit in their interior. It's not a nice place to be. It's far too hot there. You don't want to be around. But still, I want to give you a grasp of what it would sound. So let's look at stars as musical instruments for the time being. And again, here is my very simple example. You have a normal violin. Let's compare that to the sun, right? Well, then you know if you are going to play this instrument, or the contrabass, let's say, the bass will have much lower frequencies, yeah? Okay? Now, we can't resolve stars. So what do we do when we study star quakes? So the surface is going up and down with a specific frequency and amplitude. And in the interior, it's also bubbling, let's say, but we can't see that and we can't hear that. So we have to do something about it. We can see that if we have a very good detector, much better than our eyes, and we can build those detectors. But then we still have to observe the light of the star and how it quakes. And here you see a seismic determination, or measurement, I should say, in time. And so the surface, the luminosity of the star is not constant, because it has these quakes, you know. And if at a certain moment this is gas, so this moves much easier than the crust that we have here on Earth, if that material moves towards the interior of the star, it gets a bit hotter, so it is brighter, right? If it expands, it's a bit cooler, and so we see less luminosity, less energy. And that's what you see here in time. And so the way this changes is directly connected to the frequencies of the oscillations. So from measuring how the brightness of the star changes as a function of time, we can derive the frequencies. Even though we can't hear the sound, because the sound can't travel from the star to us because there's no material, right? There's a vacuum. The only thing is that, you know, this is, as I said, parts per million. While if I go to an observatory here on Earth, and even the best ones, and Spain has some of the best ones, I'll come back to that later. The transparency of the Earth atmosphere, the disturbance is typically parts per 1,000. That's really annoying. Even if we are in the best places, the Atacama Desert in Chile is typically an example. The Earth atmosphere is bothering us in this science. So how did we come to make progress? Thanks to space missions. And so I'll come back to that later. But let's first hear those sounds, because it's just fun to listen to that, okay? So cosmic symphonies is what I tend to call them. These are star quakes and the waves they introduce, and that you would hear if you were inside the star, where you can't be, but I'm going to place you for just a minute inside the sun. Yeah. So we're going to pretend as if we're inside the sun, and then you can hear the symphony of the sun. But unfortunately, I have to do another trick, because your ears are not sensitive to the frequencies. Yeah? So I have to shift the symphony of the sun as we measure it through these light variations. I shifted that to make you able to hear it. And then you can listen to the symphony and decide for yourself if you like it or not. And so if you are pleased or not by the fact that we can't hear the stars in their orchestra, let's say. Okay, are you ready? This is probably your first cosmic symphony. Is that nice? Are you happy we can't hear the sun? It's not nice, huh? Except for artists in artificial music. They love it. But it's the real sun, except for a factor 1,000,000. Yeah? And so what you see here is what I tend to call the symphony of the sun. So you see here a graph, which gives the strength of the solar quakes as a function of their frequency. Okay? And you see here, all these black lines here are musical tones that are connected with specific quakes of the sun. And what you see is that the maximum strength occurs at a frequency of about 3,000 microhertz. And if I turn that into a periodicity, then that's about 5 minutes. So the solar surface goes up and down with periodicities of the order of minutes. Okay? And so now I'll move you to another type of star. The star that the sun will become in 4 billion years from now. This is going to be the star that is going to eat the Earth. Right? It's going to swell up. It's not nice, but that's the way it is. Yeah? And so what's going to happen, I'm saying that it's going to swell up. That's moving from a piccolo, which is the sun, right, to big flute. So you know what's going to happen with the sounds. We're going to go lower in frequency. Okay? So I again multiplied with the same factor 1,000,000 to make that comparison possible. So now we're going to move to a red giant symphony observed by the Kepler satellite. Kids love this in the discos. Every open day we have a big success, because it is a real star that you're hearing. We only cheated a bit with the factor 1,000,000 for your ears. Okay? So let's look at this symphony now. Strength of the quakes as a function of frequency. Remember, the sun peaked at 3,000 microhertz, and we're now peaking here somewhere, say 65 microhertz, much lower. The star is much bigger. The instrument is much bigger, okay? So we don't listen to these sounds, but we do, day by day, analyze such diagrams, yeah? Because they come directly from the measurements. And now, of course, to complete the story, in the end, the sun is going to die as a really small, cold body, which we tend to call a white dwarf. Huh? And so we're going to listen to a subdwarf star, which is a very tiny little small star. And then you know what's going to happen. If we shrink, then we have a smaller flute, and the tones are going to go up, okay? Higher frequency. These are data that I have taken at the Canary Islands in La Palma. I'm very grateful to Spain for having that opportunity to put a telescope there. This is a subdwarf, okay? High frequency. So we can do these measurements from the ground, but the real revolution came as soon as we had the space missions. And these are unmanned space missions, just to be clear. Sometimes I get that question, when do you travel, when do you come back? We don't travel. We travel to exotic places, but not to space. Huh? And this is a cartoon of the Corot space mission. That's the French-led European space mission, launched in December 2006, and it was operational until last year. And this is the launch of the NASA Kepler space mission, which are the two instruments that really help this science to get a boost. And so here is an example of what I do in my daily scientific life. It looks like a complicated slide, but I'll get you through that. We get these nice uninterrupted data from space. Why have I highlighted the word uninterrupted? It's crucial, because we can do seismology from the Earth, as I have just given you an example, but then we must interrupt the data taking during the day, because it's light. The stars are there, but we can't see them. Okay? So we have to cut this variation in the time series day by day. So you introduce a rhythm of a day into your measurements, and that's really annoying for us. So uninterrupted space data, the satellites, once they are launched, they don't care about day and night. Yeah, they have no problem with that. And that really helped us a lot. And then factor 100 better precision, because we bring the satellites across the Earth atmosphere. So we don't have any problem with the disturbing factor that we have at observatories. Then we do mathematics, because here is a seismic measurement in time, you know, expressed in days, as you see here. And you see all the quakes of this star. And the gray band here would be the stellar light if the star would not have quakes. So then it would be completely stable. And you see all these excursions here with a blow up in between. And then we translate this by mathematical techniques to this strength frequency or strength period diagram. And all these black lines here are the tones in the symphony of the star. Okay? So then we made the step between you know, not being able to hear, but being able to measure the brightness variations. And so as you see, this is quite recent that we can do that. Now, let's look again at the sun. You have heard the sun. You know more or less. It's a bit boring, frankly, if I may say so. This is the symphony of the sun. And these are two stars measured by the Kepler satellite of NASA that are very much like the sun. So they are sort of copies of our sun, so we want to understand if they have the same physics, because that's quite relevant for us, since the sun is determining our life as well, okay? I don't know if you can read it, but here you see the maximum strength near, well, 2,200 microhertz, more or less. And here, well, a bit more than 2,500. Yeah? The sun had its maximum at 3,000. So this is a bit lower frequency, but only a tiny little bit. The red giant had only 70 microhertz. This is still very close to the sun, but not an exact copy of the sun. These stars, if we look at them from classical data, without any quakes, are exact copies of the sun. Because we can't look in the interior, because we don't have the quakes. Stellar quakes tell you immediately a much better handle on the physics, because we can see slight differences in the waves that propagate. And what does that mean? Well, the frequencies of sound waves, like I'm producing right now, they depend on the pressure, the density, and the temperature of the gas inside the star. Yeah? And you see that this is not just a random set of black lines that you see. It's very ordered, it's very structured. Yeah? So this is because the star quakes go according to eigenfrequencies of the body, as we say. Yeah? And so you see that with the other stars as well, so we get a good handle on how that works. And you see that there are patterns here, regular spacings between these peaks where they occur in frequency. And from this we can deduce information comparatively to the sun on density, temperature, and so on. Now, you can't probably see it in this graph, but some lines are thicker than others. I don't know if you can see it in these two stars. This here, for instance, this is thicker than that one. Yeah? That's because there's a tiny adjacent line, a tiny adjacent musical tone close to it. And these frequency separations are tiny, and so we need a long time base of measurements to be able to deduce them. And these are connected to discontinuities in the sound speed. So if I were to swallow or inhale some helium gas, which I sometimes do, and I would keep on talking, then my voice would all of a sudden change frequency. It would be funny. Yeah? So frequencies change according to the material of the musical instrument. And so in the core of a star, you have nuclear fusion. And so the sun is right now transferring the simplest gas that exists in nature, which is hydrogen, and it fuses that into the second simplest gas, which is helium. Right? And so where there is helium, the waves propagate in a different way. And so the helium core, when a sound wave is coming and crossing the border, it all of a sudden has a hiccup, because it needs to pass an area where the density is different, the temperature is different, and the chemistry is different. Okay? And so these small separations tell you where the position is, where the chemistry is different. And remember, I told you we wanted to know how much material was in the nuclear reactor. And astrosismology can give us that for this reason, because the propagation of the waves all of a sudden is different. Yeah? And so, if we know how much helium there is in the core of a star, we immediately know the age. Because that tells us how long the nuclear reactor has done its work. That determines the amount of helium. And the lucky thing is that we have a calibrator, because of course you need some kind of calibration. Huh? And the calibrator is the sun. Because we know how old the sun is. We know that from totally different techniques than helioseismology. Huh? I'm doing the helioseismology, but the people who study meteorites, they tell me how old the sun is. They also tell me how old the Earth is, more or less. Okay? So we have a totally independent measurement of the solar age from helioseismology, I should say, and from other means. Radioactive techniques are very helpful. And then we can see how the match is. And the match is better than 0.1%. So we have a fabulous age estimator from this. And determining the age of a star is really hard if you have no astrosismology. You basically can't do that. No. So this is really helpful. Now, this is the result from the Kepler satellites. So for the sun, we had been able to do helioseismology and set up the whole techniques in mathematics and physics to make the framework, let's say, and that was done in the 90s. And here's a diagram of energy output versus a measure for the surface temperature of a star. Huh? And then you see here, this tiny dot here where my green laser pointer is, that's the sun. Yeah? And the sun has a surface temperature of about 5,800 degrees Celsius, right? Very hot. Huh? And now all these stars, all these dots are a star for which through the Kepler NASA mission we have been able to do astrosismology. That means we have a radius estimate, remember the musical tones, big flute, small flute, we know immediately how big they are with a precision that is impossible to reach without these measurements. We have a mass, we know the material inside the star, we have a good temperature estimate, and we have a good handle on the chemistry of the star inside the star. And this is unique. We couldn't do that before. And then came another breakthrough. This was already achieved by the Corot satellite, which came before the Kepler satellite. Corot is a smaller telescope compared to Kepler. So the data have lower quality, but still magnificent compared to data from the ground. And here we could already detect red giants, which are successors of our sun. So this is what our sun will be like in the very far future. And we have all symphonies. So each telephone number here is a star. We have to give numbers to stars because there are too many. So they have very boring, long numbers in our catalog. And here you see a power spectrum. And look at this. Here is the power maximum. Here, 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 here. You see this shifting? We are simply witnessing stars. Let me give this. Normally I do exams in between my lectures, but I will not bother you with the details. The maximum here is about 70 microhertz, right? And we move all the way to lower frequencies. We go from a big star, which is called a red giant, to an even bigger one, bigger one, bigger one, bigger one, as we go from the bottom to the top. So we are watching stars grow old here. And remember, I told you in the beginning, we can't do that if we pick one star, because it takes billions of years. So by studying ensembles of stars, we can do that. Huh? And so what do we get? What we got from the Corot satellite was that red giants have quakes. We didn't know that. And this came as a very nice, well, I wouldn't call it surprise, because in my opinion, all stars have quakes, but we hadn't been able to detect them. So this opened up astrosismology for a whole bunch of stars. And then came Kepler, and here is a press release picture of 4 red giants, quakes. This is time, a slice of 20 days, and this is a big red giant, even though it looks like a small star here on the screen. That's because it becomes, as it grows older, it becomes bigger and bigger and bigger and so on. And you see that if you don't like to work with these frequencies, because that's maybe a bit too mathematical, you can just watch the luminosity of the star change. So that's the brightness change that you see. This star has this brightness change. We move all the way up. What do you see? The brightness fluctuations become bigger. The quakes are bigger. The star is bigger, so it oscillates longer. And not only that, the recurrence pattern, the periodicity of the quakes is stretched. It's as if I had pulled the time axis, right? The frequency is lower. It takes the waves longer to travel through a big star, okay? So from that, we can set the size of the star and the age, and this is magnificent. This is something we had wanted to do since very many years, and we couldn't. And then came another big surprise, because up to now, I've told you about sound waves invoked by stellar quakes. But some stars in the red giant family, they happen to have a bit of different quakes that do not only feel or behave like sound waves, but that they feel the buoyancy force, as we call it. Now, this is a difficult term, but I can easily explain that by the analogy if you are at the beach somewhere, and you know, you have the ocean, the sea has quakes, right? And these quakes do not go up and down like that, but they more or less horizontally have wiggles. These are what we call gravity mode quakes. They are determined by the gravity force. And if you combine the two, so you get sound waves, you get buoyancy waves, the two combined are what we call mixed modes. And the advantage of these mixed modes is that they propagate all the way to the center. These are the purple waves that I showed in the beginning. We have them, finally. We got there. And this is an immense privilege because these purple waves, they probe the stellar core. And that's where all the action is. So, thanks to these mixed modes, and they don't give that, normally the patterns of these red waves, the acoustic waves, in such a diagram, and you can't even read the axis, but it's not so important, you would have clear ridges. And so all of a sudden, these type of modes, there should have been a ridge if it was only a sound wave, but it's a mess. The star is sort of playing out of tone, if I would give the musical analogy. And so these mixed modes allowed us to probe the interior. Now again, there's a whole mathematical framework behind this, but let me spare you from these details and put that in an animation. So here you see a red giant, and you see the surface moving up and down, steadily, slowly, right? That's the quake we are looking at. And then these mixed modes are still having big displacements in the center of the star. So it feels the physics of the center of the star. And so by these gravity-dominated mixed modes, as we call them, you are, of course, able to say more about the stellar interior than when you have only these sound waves that propagate in the outer envelope of the star. What can we do with that? Well, we can finally, for the first time, and we can't even do that for the sun, learn something about the interior mixing processes inside stars. So what you see here is a color scale of the sun. The sun we know best. We have helioseismology. The sun does not have mixed modes. The sun only has sound waves. So we are limited to determining how the motions in the envelope of the sun occur. Now, again, I don't have an orchestra here, but surely you will be able to think about what would happen if you have a musical player on stage. He or she's playing a symphony very nicely, professional player, and all of a sudden, just to fool around, somebody backstage would press a button and the podiums would start turning. You would find it awful, because all the sounds of the beautiful symphony would be destroyed. It would be disordered. In physics, we say the frequencies are displaced with a tiny little value in practice. And the faster you rotate, the bigger the displacement and the bigger the disturbance of the symphony, right? So what can we do? We can learn how layers inside a star turn around by evaluating the displacements of the frequencies of the sound waves invoked by the quakes. Yeah? And this is what you see here in a color plot for the sun. Yeah? So here you can see that the sun, this is the surface of the sun, yeah? And we made a cut through, and you see this red here has a higher frequency than this blue here. We can see that by eye. In fact, if you want to do the experiment, it's not so difficult, but please don't look at the sun without protection glasses. Sun has dark patches on its surface, and we can see how they move. And that's in fact how we can measure surface rotations velocities of stars. Yeah? We just see the surface rotating around us. We can do it for the sun because the sun is close by and we can resolve the surface. But the spots on the sun at the equator of the sun, the centralized area, they don't move in the same way as at the poles of the sun. And that's what you see here color-coded, but deduced from the shift of the solar quakes. Yeah? And why is this white here? That's where all the activity, that's where the nuclear reactor is. And frankly, this is nice, but I want to know the colors here. I want to know how the rotation in the interior of the sun is, but I cannot reach it because the sound waves don't go deep enough. So the quakes of the sun do not allow us to test this. Yeah? Why do we want to bother at all? Because we need to know how much material is being swept in the reactor, right? Because I said in the beginning, that's what determines the life. And it's just, I always make the analogy with coffee. Those of you who like to drink coffee with milk, you take your coffee, you pour milk, you're not going to wait until it's fully mixed, right? Because the coffee is cold and it's not nice. So what do? You take a spoon and you give angular momentum. Surely you won't think about that word when you do that, but you do it anyway. You bring rotation in the game, and rotation implies mixing. And your coffee is fully mixed with the milk instantaneously. So if there is rotation inside a star, you have a fully mixed region, and you bring in new fuel into the nuclear reactor immediately and very efficiently, okay? So that's why we want to know about rotational mixing inside stars. We can't do it for the sun, but we have mixed modes in red giants, and red giants are successors of the sun. So we can do it for these stars. And this is what we have found, and this, again, without bothering you in any, with mathematical formula, that's the sun. It's going to become like this, very big. And the quakes somehow made us open up the surface, look inside, and deduce how fast the rotation is. And you see the core of the red giants are rotating faster than at the surface. This is determining how long the red giants still can live. And that's an important quantity. And so by measuring this through the star quakes, we have a first handle of how stars have interior mixing, right? And to understand that, you can compare for the evolution. I use the word angular momentum for your coffee, which is not what you spontaneously think about, but that's what we are determining here. And you do know other examples about stars. If they grow, what does an ice skater do when he or she wants to make a pirouette? And I will not attempt to do it here on stage. You open the arms, right? And then you slow down. And then all of a sudden, you pull your arms. And the better you pull, or the faster you pull, the faster you spin. And the better your pirouette succeeds. This is what's happening in these stars. Their outer layers are expanding, so their surface is slowing down, but the inner core is shrinking, and so it's speeding up. And now we have a first handle on how the speeding up is being achieved, thanks to astrosismology, and we got it totally wrong. By God, we were wrong with a factor 100 in our models, because we had a too high spinning rate. It's much slower than we anticipated. And the data are what they are. The star quakes tell us what the real answer is. So the theoreticians are not happy, but that's life of a theoretician. I'm an observer. So, coming back to the problem that we had, that we cannot watch a star in real life to evolve, because it's too slow a process, here is the latest result, a very new result, as you can see, where the internal rotation rate of 6 stars are plotted as a function of a quantity which has to do with the gravity, you know, that has to do with the mass and the radius of the star. So it's not so important that you do not know what kind of quantity it is. But A, B, C, D, E, F, that's sort of the age diagram, like growing bigger, growing older, that means. And so the surface layers, and this is the envelope frequency, it's going down. It's slowing down as the skater makes him or herself bigger. And the core going faster, spinning up. So we sort of see the aging process here of these 6 red giants. And so we have work to do, because these are, you always start, we have thousands of red giants that are observed as this, but we start with the best ones, because each one of those characters here is an immense amount of work to get that on the plot. It's months of work. So we have lots of work to do, and of course you start with the best cases, where the detection is the clearest. Yeah? And so this will be, you know, an activity of lots of astronomers worldwide. Typically, there are tens of astronomers worldwide, hundreds of them these days, because our field is growing, because it is successful. And that's just something that we have to work on. And it works. This is what we can see. Because at first, with that animation that we discovered in Leuven, that was in fact one of my PhD students, Paul Beck, who found that fast co-rotation. We didn't, you know, one star, it can always be an exception, right? That's a bit of annoying. But now we know it's not an exception at all. All the red giants that have meanwhile been done in detail, they all have that behavior. So we know what the sun will do. It's going to rotate faster in its core, but it's going to do it a factor 100 less than we thought until 1 year ago. That's quite something, because it means that there will be less mixing. So maybe it will not swallow the Earth, because this process will come to an end at one point, right? Of course, we have to try and understand that better, but this is one of the key results from astrosismology so far. Now, what else can we do? Well, we can do many things. As I said, we have thousands of stars yet to be analyzed, and here's a sort of a map of our Milky Way. Yeah? So here's the sun, and this is just a coordinate system of projection, and all these colored bars here, these are all stars that have been observed meanwhile by the Corot and Kepler satellite. And so we don't only have single stars, we have all sorts of objects. Multiple systems. Some stars live with a companion, or with triple systems, or a whole cluster. And so we can understand them. And what's the advantage of studying stars in a cluster in seismology? Well, if stars are in a cluster, then they were born together at the same time. So they must have the same age. So this helps us to put more stringent constraints on the physics. And so we are watching stars by their quakes in very different areas where we look inside the galaxy. So this tells us something about the ages of stars surrounding us in very different regions of the galaxy. So people who study galaxy dynamics and galaxy aging are, of course, now looking towards the ages that we provide them from seismology. And we're also looking at different direction. You know, our galaxy is not flat, it's a spiral volume, let's say. It has sort of a disk, as we call it. But, you know, above the disk, or really in the middle of the plane, stars have been born at different epochs and with different metallicities. Because as the stars grow old, these old stars, I call them the metal factories of the universe. And by the way, you should be very grateful, because all the carbon and all the oxygen and all the nitrogen in your body was made in a supernova explosion. You may not think about it like that, but it's true. And so you should be grateful to the stars. And so the level of metals is by having different generations of stars having exploded. And so now we have a better handle on how often that happens, because we can do the aging much better, okay? So we wrote a book once, and it seems like ages ago, but it's only 5 years ago. And since these 5 years, I must say, this is very sad on the one hand, and I'm very proud of it on the other hand. We had written this book prior to the launch of Corot and Kepler. Yeah? The theory is still the same, but the observational facts have changed quite drastically. We have moved from parts per thousand, which we can do from the ground, to parts per million. That's a factor 1,000 better, thanks to these two missions. We have moved from a few bright stars, you know, I had a handful of stars before the launch, to thousands of them, and we have all their ages, not yet determined, because we have a lot of work still to do, but we will get there, you know, in several years from now. And so we could do physics in stellar envelopes, like for the sun. It has quakes that probe only the outer envelope. But now we go straight through the cores of the stars. And we have a first handle on the internal rotation. So that's magnificent progress, I should say. And this is simply a new way of doing stellar physics by astrosismology. And so this is really nice to be able to work on this field and to have space missions. And I'm very grateful to the European Space Agency for helping a little bit here. So where do we go from here? There is a lot of work to be done, but we are not going to sit and wait and do only the data that we have from Corot and Kepler. What we would like to do is combine that with ground-based data. Now, I just told you from the ground, the seismic data, they are not fabulous, and they certainly are not what can be done from space. But an interesting fact is that we can do something else, and this is expressed by this picture here of the very large telescope of the European Southern Observatory. This is situated in the Atacama Desert, and these are big telescopes, more than 8-meter diameter each, and as you can see, they have been placed on a mountaintop in a very weird, seemingly weird way, but that's to improve the resolving power. So we can resolve stellar surfaces. Huh? You can't do that by eye because the stars just look like a tiny twinkling dot in the sky. But if you can combine the light of these 4 telescopes, and that's being achieved by tunnels underneath the ground, then you can have positive interference and you increase the resolving power as if you were to have a telescope with a diameter that encapsulates all 4 telescopes. And we start to resolve stellar surfaces. This has been ongoing since about a decade, but we can't really yet measure the radii of stars that are small. We can do it for some red giants if they are close enough to us, but we want to do that for the stars where we have seismic data. And with improving instruments, we may hope to get there one day. As already alluded to by Martin Kessler, we are eagerly awaiting data from the ESA cornerstone space mission Gaia. Gaia is a space mission that has been launched successfully. It's being commissioned for this moment. So that means that the engineers are trying to understand what the data tell us. After tests in the lab, you also have to test your satellite after launch from space. And Gaia will give us the distance to 1 billion stars in our galaxy. And so if you have a distance, then you can translate the luminosity, the strength of the light of the star to a true energy output. Because, you know, it's like with lamps. If I have a 10-watt lamp here and I have another one a kilometer away, the strength is the same of the energy output, but you observe it very differently. You observe it very faintly. So it's the same with stars. The luminosity of the star, the brightness of the star, it depends on the distance. And if you don't know the distance, then you don't know the real energy. And the real energy is connected to this nuclear plant inside the star, frankly. So Gaia will deliver distances, and connecting those with the luminosity that we can measure from the star, it will give us the radius. Because the luminosity is connected with how big the star is and how hot it is. Now, how hot it is, we can measure fairly well from the ground, but how big it is, we can't do, except for stars with seismic data. And then Gaia will give us an independent measurement of the radius through its distance, and we can confront the two with each other. And this is going to help us a lot to see how to make progress. And then here I cannot resist by commenting on the fact that we are astronomers. We love space missions, but still space missions can't do everything. I come back to Corot and Kepler. They measure stars continuously, but Corot measures the stars like every 12 minutes. We have a brightness measurement. Kepler measures the stars every 30 minutes. We have a brightness measurement. For Kepler, we do that 4 years in a row without interruption. For Corot, we could only do it for 5 months in a row. But what about stars that quake at a cadence of 20 seconds? Well, if you have a measurement every half hour, it's not going to get you anywhere. So there are stars, the piccolos, the very small musical instruments, that we cannot do with Kepler or Corot, and that we can do from the ground if we have dedicated instruments and if the periods are much shorter than a night. Because then we see the quakes going up and down frequently enough during the night. And so at the Mercator telescope, which you see here, we have built such an instrument, and it has been inaugurated a few weeks ago, specifically for the study of astroseismology of very tiny little compact stars. And this instrument is called MAIA. It stands for Mercator Advanced Imager for Astroseismology. And the nice thing is that this telescope is situated on the Canary Islands in Spain, right? And we have a very good collaboration with Spanish institutes who want to use the instrument. We can put our building in the observatory, they can use our instrument, and we can collaborate. So this is very nice for us Leuven scientists, I would say. So another thing for the future, and that brings me almost to the end of my talk, is what will we do next? We will move towards doing seismic studies of systems like our solar system. So the sun has a planet called Earth, and we happen to like it here. And of course, the question is, are we alone? How unique is this system? Are there other systems like that? And in particular, are there planets that would be able to sustain, to initiate and sustain life? That's a question that I guess every human being, is interested in the answer to that question. Let me put it like that. And so the habitable zone of stars is something we want to study. What is a habitable zone? Well, that's an area adjacent to the host star that has planets surrounding it, where it's comfortable for life. Yeah? Of course, we have to define what that means, life, and we only have one example, right? That's us here. Yeah? So we tend to be a bit, narrow-minded in that respect because we have no other experiments. So what we want to do is study a lot of stars, like the sun, that are quiet, not violent, not exploding stars, because there will not be life on planets there, and then find out, do they have planets? And if so, are these planets situated in a good area to have something that could be liquid water? Because that's what we, connect to life as we know it here. And of course, it depends on the star. So for a sun, we know what the habitable zone is because we are inside it. And the planet Mars is also inside it, if we define that. So maybe Mars had life before and it's gone now. That's a matter of aging, right? And so for bigger stars, more massive ones, the habitable zone is a bit further away. It's hotter, so you need to be a bit further away to have a comfortable situation. On the other hand, for cooler stars, well, you can be a bit closer in to still have something what could be liquid water. So how do we find them? Well, we're going to find them thanks to a new space mission project that's called Plato. This is a European Space Agency project, so it's European. And this mission is going to hunt for planets around other stars that also have star quakes, because that delivers us the radius of the star, which you need to find the radius of the planets. And that gives us the age of a star, and we need to be in a good age range to have conditions for life. Plato is going to be launched, as you can see here, in 10 years from now. That's the way space science is being done. You get up a project idea, you work on it, you try to come up with a machinery that can do what the scientists do. It's a magnificent interaction between engineers and scientists. Very funny sometimes, very tough sometimes, but it's very interesting. And then once you have passed all the advisory boards and you're the best mission project, then the European Space Agency says, yes, we're going to build it. And then you can start building, and it typically takes you 10 years to build that, because this instrumentation is not something you buy in the supermarket. This is high technology helps development, and it just takes that long. And then to find planets around stars, this is an artistic impression. This is not a real measurement for the sake of clarity. Then you need to observe how long? Well, years, because we on Earth travel around the sun in 1 year, right? And that gives you what we call a transit event. So if the Earth passes in front of the sun, then the light of the sun has a little dim. Maybe you have seen that already with Mercury or Venus. It goes in transit in front of the sun, and the solar luminosity drops. How much? Parts per million. What do we need to study star quakes? Parts per million. So we can do this together if we come up with a clever design. And that's what Plato is going to do. And then we're going to screen about 400,000 stars to look for planetary systems. And then we will deduce masses, radii, ages, and also properties of the planets, but we cannot deduce with the same space instrument if there is life or not. For that, we need to understand how the atmosphere of the planet behaves. We need to do chemistry of the planet when it's in transit in front of its parent star. We need another space mission for that. But I'm sure that once we have good candidates, we will get through the advisory boards and hunt for signatures of life, because that's really what is very motivating and stimulating. So we are not yet there. We will always need ground-based data to complement the space data, because we need the temperatures of stars. So to end up and wrap up this lecture, a cartoon to show you we shouldn't screw up our own planet, because we need some time here for us, but also for our children and our grandchildren. So be green, please, because even though we have Plato now in the pipeline, it's not going to be like we're going to jump on close planets around other stars. We will not be there so fast. Even if we find them, we will have no way to travel to them. So be kind to our planet. And to really round off, our planet is also a place where we have Earth symphonies. So to finish, I'd like to take you to the Mercator telescope on the Canary Islands, so that you can get a feeling for what the, I wouldn't call it daily life, but still the environment is that astronomers like to work in. And since this is Spain, I thought it was nice to round off with this idea. So let's look at, or listen and look at some earthly symphonies, as I call them. This is not about earthquakes, but this is about impressions at La Palma Observatory. This is a composition that was made by one of my former PhD students, now a postdoc. And it's just a relaxing way to end this talk. It's a 2-minute movie, so I hope they can dim the lights now and that you can enjoy it. a great pleasure to be in Madrid. We enjoyed it a lot the past days, and I thank you for your attention. I hope you learned something tonight.